Okay, so now let's look at a sort of typical projectile problem. And on this problem, we're going to launch a cannonball off a cliff. This is the cliff. It has some elevation, and we're going to say this elevation is 100 meters. So the top of the cliff where the cannon is fired from is 100 meters off this ground right here. And so we have a cannon that's going to shoot a cannonball, and it's going to have an initial velocity of v naught, and it's going to make an angle right here of theta with the horizontal. And we're going to define v naught as 300 meters per second, and this angle theta is going to be 20, an angle of 20 degrees. So some things we might be interested in finding out are, if here's what our projectile path is going to look like, and this is our maximum altitude, so our maximum height, maybe something we might ask is, what is this height? How high does this projectile actually get off the ground right here? Another question we might ask is, if this is where we start from, how far does the projectile actually go? What's this range? And a range is going to be how far the projectile actually fires. And maybe in working with how high this is, what's the time it takes? What's the time it takes to get to this maximum height? So here's three things that we might ask ourselves, and here's pieces of information we're given to start the problem. And how do we go about finding these three unknowns? So first, let's figure out our x and y components of velocity. So if we look at what we're given an initial velocity v naught is equal to 300 meters per second. And we know that we're going to have an initial x velocity. This is going to be our velocity, our initial x velocity. And we're going to have an initial y velocity. And this is going to be our v naught y. And if this is given, like we said, an angle of 20 degrees, we know that v naught y is going to be equal to, this right here is going to be equal to 300, so v naught, times the sine of this angle, so times sine of 20. So sine of the angle, and this is equal to 300 sine of 20 degrees. And if we perform this calculation, this is equal to 102.6 meters per second. And if we do the same thing for our initial velocity in the x direction, we have an initial velocity in the x direction is equal to v naught times cosine of theta, and so 300 times the cosine of 20 degrees, and this is equal to 281.9 meters per second. So that means that our initial velocity in the x is moving at 281.9 meters per second, and our initial velocity this way is 102.6 meters per second. And in case you don't believe that, if you decide to figure out the magnitude, what this v naught is, you would say 102.6 squared plus 281.9 squared, and if we're taking the magnitude, so if we take the square root of this is going to give us 300 meters per second that we had to begin with. and this is our v naught. Okay, so this is good. We have our velocity broken up into our x and y coordinates, and if we look at this a step further, if we look at our vertical direction, we can use our kinematic equations and try to figure out how long this projectile will be in the air for. So if we do this, we have our final position is equal to an initial position plus the initial velocity in the y direction times time plus 1/2 times the acceleration times time squared. So what's this acceleration term right here? Well, this is a projectile problem, so our acceleration is going to be gravity. And gravity is going to be, it's opposing our positive convention, which is going to be up. This is going to be our positive direction. And gravity is going to be negative 9.81 meters per second squared. So if we plug in everything we know into this equation right here, we have a final position, which is 0. And we're calling this 0 because we're going to say this right here is our origin. So this is 0, this is 100 the cliff is 100 meters above 0. So our initial y position is going to be 100. It's 100 meters above our origin, plus our initial velocity in the y direction, which is 102.6. And we're solving for time, so it's still an unknown. And then we're going to put in our acceleration. Here's the minus sign, minus 9.81. It's being multiplied, so we can just move the minus sign out front. And we have a time squared. So we have to solve this equation right here for time. And we know we're going to get 2 roots of time because it's a squared term right here. And if we use our quadratic formula or any other solving type method you want to use, the 2 roots we're going to get for time, we're going to get time is equal to negative 0.93, negative 0.933 seconds, and we're also going to get 21.83 seconds. And we know that for our application right here that we're not interested in this negative root right here because it's time. This means it happens before our launch, and it's not really what we're interested in. So we know that the time it takes for the projectile to hit the ground from 100 meters above on the cliff is 21.83 seconds. That's good. So now if we look at our horizontal components, our x direction, we can figure out what our range is. So our final x position is going to be our initial x position plus our initial x velocity times the time, which we just found. So this final x position, which is our range, it's going to be right here, is going to be equal to our initial x. Well, our initial x is 0, plus our initial velocity in the x direction, which is 281.9, times this time, which is 21.83. And if we figure out what x is, we'll get an answer of 6,153.9 meters. So the total distance this projectile travels is 6,153.9 meters. So this range is, this distance right here, 6,153.9. Well, that's great. And that's the first part of what we were trying to figure out. And now the second part is how long it takes for this projectile to get to a maximum height, and what is that height. Now, the trick to figuring this out is we know when a projectile is at its maximum height, its velocity in the y direction. So right here, the velocity in the y direction is going to be equal to 0. And we know this because it's no longer climbing, it's no longer getting higher, and it hasn't just yet begun to fall down. And we also know that the velocity in the x direction never changes throughout the entire flight. The velocity in the x direction is always going to be its initial velocity. So in order to figure this out, we can look in our vertical direction again. We use our equations from our vertical component. And if we know its final velocity is 0, and we know its initial velocity is its 102.6, we can use the equation Vf is equal to V initial plus AT. And we know everything here except for time. So if we solve for this equation, we get our final velocity is 0 is equal to our initial velocity, which is 102.6 minus 9.81 times some time. And this time right here is the time it takes to get to its highest point. And if we solve for t, we're only going to get one root this time because there's no squared or cubic terms or whatever. It's just a t. And we're going to get a time that is equal to, a time that is 10.46 seconds. And this 10.46 seconds is what we're looking for, and is how long it takes before it reaches its maximum height. And the last part that I wanted to figure out was, what is this maximum height? Well, if we're still only worried about the vertical direction because this is just y, if we want to know what a final distance is, so y is equal to an initial height, which is our initial height, plus an initial velocity, plus 1/2 times the acceleration times time squared, we get the initial height is 100 meters because it starts on this 100 meter cliff. The initial velocity is 102.6 meters per second. Because we're interested in how long it takes to get to a maximum height, the time it takes to get it to its maximum height is 10.46 seconds minus the 1/2 times the acceleration, which is 9.81. And this time is the same as this time, so it's, if this all fits on the page, 10.46 squared. And when we solve, we just add up all these terms, and we'll get the height is 636.5 meters. And that is from reference to the ground. If we were interested in how high it was from the top of the cliff, we'd subtract that initial 100 meters out, and we'd get the height that this rocket has gone from the top of the cliff is equal to 536.5 meters.